Hello everyone, my name is Said Damadi and I'm going to present the backpropagation algorithm for a math student. I'm going to present this paper on behalf of my collaborators at Department of Mathematics and Information System at UMBC, and this is the presentation of our paper at International Joint Conference of Neural Networks. Well, backpropagation algorithm is the fundamental algorithm for training every supervised neural network, and it is very useful because every algorithm uses backpropagation algorithm. And the theoretical advantage of backpropagation algorithm is that the complexity of calculating the gradient, it does not increase with the number of layers. And we wanted to give a proof for backpropagation algorithm that is consistent with tools such as PyTorch, and it preserves the clarity and the cleanness of mathematics. That is why I started writing this paper. For training a supervised network, we pass an input x and then we get a y hat as the prediction, and we are assuming that deep neural network has the parameter vector of theta. Once we have that, we measure the error between the actual label and the label that we have predicted, and then we take the gradient of this loss function. And why do we need that gradient? Because we want to use a stochastic gradient in order to get to a local minimizer and have a trained network. Backpropagation comes into the picture when we want to calculate the gradient of this loss function. Although it is a scalar function, but it might be a huge function with so many parameters, so calculating the gradient is a bottleneck in training a neural network. That is why we use backpropagation algorithm. And in order to calculate the gradient, we need to observe that we can separate the last layer activation function from the network, and then we can use the relationship between Jacobian and the gradient to simplify the calculation, which I am going to explain in the next slide. By separating the last layer activation function, I mean F capital L, which is the last activation function, so we can just separate this out and use the output of the last layer, and this helps us to rewrite the loss function, which is loss of y and y hat, and then include this last layer activation function. Once we have this, we can simplify the gradient of this loss function, which is this one, into two terms, and we can efficiently calculate these two things, which I'm going to explain in the next slide. This lemma shows the relationship between gradient and Jacobian of a scalar value function. So we can just write the gradient of a scalar value function as the transpose of the Jacobian, and then we can just rewrite this and rewrite this as the Jacobian of the function, including the last layer activation function. And because we are doing Jacobian, chain rule can be applied, and then we can separate these two out and first take the Jacobian with respect to ZL, and then take the Jacobian with respect to theta of ZL, because chain rule applies. And once we have these two, then we can apply the transpose and then put this one first and this one for the second term. And this second term, because L is a scalar value function, this ends up to be a gradient, and this one is the Jacobian. And we'll see how we can calculate this efficiently, because the last layer activation functions for different neural networks are very well defined functions. So here we want to address that second term, which is the gradient of this loss function with respect to ZL. And this is easy to calculate because we have a sigmoid function or a softmax function or identity when we are using mean square error. When we're using a softmax function for classification, we use cross entropy function, and when we use binary classification, the error is going to be a sigmoid function. So we are dealing with these three functions. Each one has its own loss, and then we can calculate the gradient with respect to ZL. And if we do that, we get a difference between y and y hat for the first two losses, and -2 times y minus y hat as the gradient of the loss function with respect to ZL. For the proof of all of these gradients, you can confer to the appendix of the paper and see the detail for each one. Well, in order to give an example, we use one layer network to calculate the gradient of the loss for classification problem. We have a network that has only one layer. This is very important because one layer can be thought as the last layer of a neural network, and it is very useful to address this. So we want to calculate this gradient, and we want to split the gradient into this one and this one. The last one is the gradient of the loss function with respect to z, and the first one is the Jacobian. We'll see how we can use them in next slides. Well, we first want to calculate this one, and this is super easy because we can convert to table 1 and find this one because there is a softmax function here, and then we can just calculate this one. Only notice that theta is going to be vectorized version of W, and this is putting the columns of W matrix so that the first column would be on the top, and this is only vector B, so we can have the parameter vector of the neural network, and then we can find the gradient. Remember that we calculated the second part, and now we want to find the first part, which is Jacobian, and then we take the transpose of this and multiply by the second part in order to get the gradient. Notice that z is the function of W transpose times x plus b, and this can be broken into three terms, and each term involves each column of W matrix. So once we have this, we can simplify the Jacobian and then find the Jacobian. Here we see the matrix is going to be with 3 rows, and because we have 3 outputs, and we have 15 elements for each vector on the row. 15 elements is that because we have 12 W's and 3 B's, and that's why we have a matrix which is 3 by 15 as the Jacobian. Once we take the transpose of this and put it here and multiply by the gradient with respect to the output of the last layer, we finally get the gradient of the entire network, which is this one. Notice that this is only function of x and this is only function of y, and I'll show you for the famous network, famous problems with a single layer, how we can observe this fact again. Here you can see famous problems as one layer neural network, and simple regression, linear regression can be written as L equals y minus y hat, and we can have each sample as x, and then we have a weight and bias, and then we end up with this gradient as a function of x and 1 and y minus y hat, which is consistent with what we had for one single layer. Also, simple binary classification, we have a sigmoid function, and then for example this is going to be the loss function, and then we have a function of x and a function of x times y minus sigma of theta transpose times x, which is going to be our y hat. And if we go to multiple linear regression, we can define multiple linear regression as a single layer neural network, and this is actually can be found using the gradient that we just developed, and we can see this as, only as a function of x. And then once we have a logistic regression that involves sigmoid function, then we get the same thing, negative of a function of x times y minus y hat. For the proof of all of these, you can confer to the appendix of the paper. Now let's see what happens to a two-layer network. So we said that we separate out the last layer activation function, and then we have two layers, and we want to calculate the gradient of this neural network. As we saw before, we separate this gradient into transpose of the Jacobian times the gradient of loss function with respect to the output of the last layer. So this one is easy because we can just go to the table 1 and then get this because there is a softmax function and we have a classification problem. Theta is the vectorized version of W1, B1, vectorized version of W2 and B2. So now we want to calculate this Jacobian, which is going to be a matrix, and we'll see how we can find it. The Jacobian that I was talking about can be broken into two Jacobian. Jacobian with respect to parameters of the first layer, Jacobian with respect to parameters of the second layer. And for the second layer, notice that we have W2 transpose times A1 plus B2, and then we want to take the derivative with respect to W2 and B2. This is going to be this matrix, which is very, very similar to one layer neural network, which I said that it can be thought as the last layer of a single layer neural network because the form that you see here is consistent with a single layer neural network that we already had. We saw that we calculated the second term. Now we want to calculate the first term. For the first term, we want to find the Jacobian of Z2 with respect to W1 and B1. So we rewrite the formula of Z2, and because B2 is not a function of W1 and B1, we can just ignore that, and because W2 is a constant term, we can just take it out because it's not a function of W1 and B1, and in that sense it is a constant term. And now we end up with finding Jacobian of A1 with respect to W1 and B1. Activation function of the first layer is the activation function applied on every output of the first layer, so we want to calculate this Jacobian. In order to calculate this Jacobian, we can again use the chain rule and first calculate the Jacobian with respect to Z1 and then find the Jacobian of Z1 with respect to W1 and B1. This formula is very familiar to us, and then we can calculate this, and you recall that this is going to be this matrix, and we only have this Jacobian. This Jacobian, when this F1 is a ReLU function, becomes a diagonal matrix, and on that diagonal matrix we get many zero elements, and those zero elements are for the output whose value are less than 0 or equal to 0. Now we have everything. This part gradient is y minus y hat with negative sign, and we already calculated the two terms of this, and we transpose them. We get this, and this is the structure of the gradient. And as I mentioned, this is a diagonal matrix when it is the activation function for the first layer is a ReLU, and for all zeros on the diagonal of this matrix, we remove every row of this W, and you see a lot of zeros here, and that is why we can parallelize this and calculate the gradient efficiently on GPUs. Here is LINET 100-310, which is used for MNIST classification, and it is actually a network that can classify MNIST dataset and classify digits very efficiently with accuracy of 98%. And we can do the same thing and separate out the softmax function and do whatever we did before. So we start with the gradient in terms of two terms. We calculate this gradient from the table easily with this. We notice that theta is the vectorized version of all the parameters, and then we have three terms inside of the Jacobian. The last one is for the first layer that has more matrix multiplication. This is the second one, and this is the first one, which is very similar to the first layer, as we already mentioned that. Now one may ask how we can apply this method to convolutional neural network. To see that, just consider this image with a filter. The output of the filter is going to be an image with 4 pixels. That's why we have 4 rows here. We can convert convolution to matrix multiplication using Toeplitz operator that puts the elements of a filter in an order that Toeplitz matrix does, and then we can apply that, and we'll see using a lemma. This lemma shows that we can rewrite a convolution operator as a matrix multiplication by using Toeplitz operator and then vectorized version of the input, so we can convert a convolution into matrix product, and then we can apply whatever we apply to fully connected networks. And here is the algorithm, and we can just let the input be A0, and then we can find the Jacobian terms, and we can also calculate the second term of the gradient from table 1 and come up with the gradient of a neural network very efficiently. Thank you for your attention, and I hope you enjoyed the presentation, and this proof can help you to come up with better understanding of deep neural networks.